This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning everyone. So, picking up from where we left off last time, let me just go through the example we were doing because it ended up being a bit rushed and I lost track of time and we ran out of time. So, we were just looking at this example which followed on from our discussion of the impact of modelling error and what we can do to deal with that. So, in this example we have a plant that it has two stable poles, one at s equals minus 1, one at s equals minus 2. And what we're trying to achieve here is tracking of a step reference, okay, rejection of an input disturbance, which is sinusoidal. Okay, we know the frequency, but we don't know the size, and we don't know the phase. Okay, and that's consistent with thinking of these external signals as sometimes representing uncertainty, things that we don't know about the operating environment. Okay, our model is not exactly what the real system is. But let's suppose that we know that the real system is related to this model via a multiplicative perturbation with size that is bounded in the way shown here. Okay, so the size of the multiplicative uncertainty depends on frequency, and as we saw before, multiplicative modelling uncertainty is typically more significant at high frequency than at low frequency, and this dotted line shows what this bound is, and it shows that there's more uncertainty at high frequency than at low frequency. All right? So, our closed loop system looks like this. So we've got a reference coming in, goes into our controller. We've got an input disturbance, DI. This is that sinusoidal signal with uncertain amplitude and phase. We have our nominal plant model, okay, and we're feeding back a measurement of the output. Okay, so this is your reference, this is your error signal. All right, we're trying to make Y track R. All right, in other words, we want to make the error signal insensitive to the reference, and we want to make the output signal insensitive to the input disturbance. Okay, so what's being proposed is this controller, okay, and the controller has two zeros which cancel the two stable poles. That's okay. Stable pole zero cancellation is okay. All right. And then there are two more zeros. All right. There's a pole at s equals 0. That's associated with making sure that the sensitivity function that tells you the relationship between the error and the reference will have 0 gain at 0 frequency, as required to get 0 error in steady state for a step reference. Okay. There is a pair of poles at s equals plus and minus j. As we'll see today, that is consistent with rejecting an input disturbance of frequency 1, okay, in terms of its effect on the output signal. All right. And there is another pole at s equals minus 100 to make sure that we're rolling off at high frequency so that the complementary sensitivity function will have small gain at high frequency as required to reduce the sensitivity of the closed loop to high frequency measurement noise, but also to make sure that we're robust to this modelling error. As we saw last time, in order to get robustness to this, we need to make sure that the product of this and the complementary sensitivity function is less than 1. Okay, and if it's much, much less than 1, then the perturbed closed loop will be very close to the original, the closed loop that you get when using this as the plant model in terms of how the sensitivity functions are shaped across frequency. Okay, so I haven't explained what these zeros are doing, right? I've explained what all of the poles are doing. I've explained what these zeros are doing. What are these zeros doing? Well, these zeros are there to make sure that we have a reasonable phase margin at the crossover frequency. Okay, so this is limiting the crossover frequency. Okay, we've got to choose a crossover frequency that is below where this becomes significant to make sure that T will roll off. Okay, so that's how we decide where that should be, right? It's really determined by this, and where the multiplicative modelling error is becoming significant. All right, this is there to get the disturbance rejection. This is there to track the reference. Okay, so why do we need these? Well, let's think about what the open loop transfer function looks like. It looks like this once we've cancelled the two stable poles. Okay, so this is giving us this very high gain at low frequency as required to make the output sensitivity function 0 at 0. Okay, and this term here will look like, you know, this, and then go down at 40 dB per decade beyond the frequency 1. Okay, so you can see that it produces this peak here in the loop gain, okay, which again forces a sensitivity function to be 0 at the corresponding frequency. But the phase of this is such that it starts at 0 and it quickly changes to minus pi. Okay, and so what it does to the phase of the loop transfer function, which starts at minus pi on 2 because of the pole at the origin, it kicks it down below minus 180. Okay, so what the zeros here are doing are bringing the phase back up above 180 to give us a positive phase margin, to give us a phase that sits above minus 180 at the crossover frequency. Okay, those zeros, each of them contributes pi on 2 radians a phase across frequency. All right, so having two of them there is bringing this back up. Okay, it also flattens off. Okay, so with this pole here, this will start going down at 40 dB per decade, right? And these two bring it back up again, right, to flatten it off so that it doesn't keep going down at such a fast rate at crossover. All right? So, you know, we often do things like this in control system design, add poles and zeros to the compensators to shape the open loop transfer function in order to get the right crossover frequency, in order to get high gain at the right frequencies, and in order to get the right phase margin. Okay, this is loop shaping design, or an example of it. Okay, so what we're going to look at today are some fundamental limitations associated with the structure of feedback control systems in order to identify some trade-offs that are relevant from the perspective of how to shape the open loop transfer function across frequency. And in part 4, okay, we will be focusing entirely on how to shape the open loop transfer function in order to meet control specifications of the kind that we've just discussed. Okay. The bottom line is that control system design is about balancing off these competing objectives, okay, as we've already discussed. So this is just a summarise of all this stuff. I just want to point out there's a typo there. Somehow the minus sign went missing. Okay, I'll leave that for you to read. Okay, but as we were discussing last time, you know, control system design is about balancing off competing objectives. We've looked at performance in terms of reference tracking and disturbance rejection, and we've seen that that typically leads to a lower bound on the crossover frequency. Okay, the loop shape typically looks, in terms of the gain, something like this, okay, where lambda is large at low frequencies. Why? Because that makes S small, right? And the sensitivity of the error signal to the reference is determined by this transfer function, right? And if the reference has most of its energy at low frequency, we want to make sure that this transfer function is low at low frequency, so the error will be small. Okay? How can we make this smaller? Well, we can push the crossover frequency further to the right. One way to do that is to increase the gain, right, which will shift everything up by the same amount at every frequency. And if I do that, it'll make the sensitivity smaller, right, over a wider range of frequencies. Okay? And the same goes for output disturbances and input disturbances. Okay? So trying to meet these sorts of objectives is translates to trying to push the crossover frequency further to the right. Okay? So in other words, they lead to a lower bound on the loop gain crossover frequency. Okay? Whereas consideration of sensitivity to measurement noise and sensitivity to multiplicative modelling error translates to an upper bound on the crossover frequency. Okay? We know that those things are determined by the complementary sensitivity function. Okay? And the complementary sensitivity function will be 1 where lambda is large, but it'll be small where lambda is small. Okay? And to get low sensitivity to measurement noise and low sensitivity to multiplicative modelling error, we want T to be small. How do we make sure T is small? We make sure that at frequencies, the crossover frequency is sufficiently far to the left of frequencies where there's significant measurement noise or significant modelling uncertainty. Okay, so those things lead to upper bounds on the crossover frequency. This is what I mean by a trade-off. One thing's trying to push it that way, the other thing's trying to push it the other way. Right, that's an example of a trade-off. Okay. Similarly, trying to deal with actuator saturation and rate limit problems leads to an upper bound on the crossover frequency, and that relates to not ending up with too much peaking at the crossover frequencies or too much gain at high frequencies in the control transfer function as may be required to try to push the crossover frequency to the right. Okay, so we're trying to balance all of these things off against each other in control system design. And really these are determined by the nature of the external inputs to the system and how they have their energy distributed across frequency and the nature of the modelling uncertainty. Okay? And these are managed by separating the competing objectives across frequency. That's what I'm saying. These are low frequency signals, these are high frequency type things. That's how we separate the competing objectives, right? And we can deal with them by just making sure that the open loop transfer function has the right shape across frequency. It has high gain at the right frequencies and low gain at the right frequencies. Okay? And in addition to this, there are some structural limitations that limit what can be achieved with a feedback interconnection by virtue of the structure of a feedback interconnection, as we'll see today. Okay? So the first example of a structural limitation is delay in the loop. Okay? So let's consider a situation where you're trying to reject a plant output disturbance. So in other words, make this signal insensitive to this signal here, right? Where this signal here is the output of the plant. And let's just consider the case where it's a pure delay. So the plant is just a pure delay. Wiggling this signal here is seen at the output after some time, right, with delay. So let's think about what the best thing we could do might be, all right? So if I am measuring this as part of my feedback, okay, if I know what the input is, I'm generating that thing, if I just put that through a delay, right? And so this signal here becomes like this signal here, right? This signal here, let's call this y hat, is just d plus y hat, okay? So if this is y hat, okay, and I subtract that away from d plus y hat, then what I get here is d. So by doing this, I've effectively reconstructed the output signal, okay? And so what I could do is just now feed this back, okay, compare it to your reference, and then feed it forward like this. Let's just, for the sake of argument, say the reference is 0. So we're trying to make this signal here equal to 0, okay? And if you like, this is our control, right, which is drawn in the dotted box here, right? So this is just redrawing the picture that I've shown, okay? Well, let's think about the situation where D is just a step in time, okay? That's not a very straight step. So D just being a step, all right? Now, no matter what control action I take, it's only seen after some delay. Okay, so I can do this, I can reconstruct my step here and put it in here, and what I'll get out is some delayed version of it. All right? In fact, what we should do is make it, we're making it minus d here, okay, because it gets multiplied by -1. So we're putting minus d through here, but it comes out after some delay, so d will be like this, y hat will be like this, some delayed version of the disturbance, okay? But you can see that when I take, well, it'll be minus, sorry, y hat will be minus d, right? Okay, you can see that when I just add those two together, the result is that I initially get some effect of the output disturbance on the output signal y, but then in steady state it's 0. Okay, so in some sense this is the best I can do, okay, given that whatever I do here is going to be delayed. All right, so for a very low frequency input, this seems to be a sensible approach, okay? But what happens if I now consider a sinusoidal signal here? Okay, if I consider a sinusoidal signal here, I'm still reconstructing the disturbance here with this controller, okay? And so I'll get a sinusoidal signal here. Putting a sinusoidal signal through a delay shifts it in phase. Right? What happens if I delay a sinusoid, right? So what we'll be getting is D doing this, all right? And the thing that we're reconstructing at the output of the delay will be minus this, but shifted in phase, right? So it'll be shifted in phase such that when we add them together, they won't cancel each other out. Okay, unless the shift in phase is an integer multiple of the period, then they'll cancel each other out. Okay, but if the period is very long, then the shift in phase will be such that the sum of the things is small. All right, so that's the basic idea behind saying that this is the best we can do, okay, when there's delay in the loop. Use a controller like this that effectively reconstructs the disturbance and then just passes it through the delay. Hopefully the phase shift is sufficiently small relative to the period of the disturbance such that they cancel each other out. Okay, if you look at the sensitivity of transfer function from here to here, it has this shape. Okay, the sensitivity function for this controller just looks like this, and the magnitude plot looks like this. So you can see at low frequencies, the gain from here to here is small, as we saw intuitively over here. Okay? But for high frequency signals, the gain can be large. All right? Because when the reconstructed disturbance goes through, the delay gets shifted in phase. All right? Unless that shift in phase is exactly an integer multiple of the period, there can be significant gain from here to here. All right? So having delay in the loop is putting a limitation on the range of frequencies that we can reject at the plant output. We can do a reasonably good job of rejecting, attenuating the effect of output disturbances on the output at low frequencies, but high frequencies we can't do it. Right? So this is a structural limitation associated with having delay. All right? This point at which the gain from here to here becomes 1 is related to the delay. It's related to 1 over the delay. Okay, so having delay in the loop puts a limitation on the crossover frequency. Okay, this point here, as we've seen before, is where the loop gain will cross over. All right, and as we've seen before, having delay in the loop places a limitation on the crossover frequency from the perspective of stability, right? Because we can't have too much gain. If we have too much gain, then the critical point will be encircled. And if we keep up pumping the gain, we'll change the number of encirclements required for closed loop stability. So we've already seen this sort of stuff before, but now we're just thinking in terms of output disturbance rejection. Okay. Also, with this controller, which is in some sense the best we can do from the perspective that we outlined here, the complementary sensitivity function is just flat, right? It never rolls off. All right, so doing the best we can from the perspective of rejecting the disturbance will give us a closed loop system that is very sensitive to measurement noise. So if we've got errors in the thing that we're feeding back here, this won't work, right? And it will be very sensitive to modelling error, okay, including error in our model for the delay. So if we have parametric uncertainty in the delay, as we saw by example, that would correspond to a multiplicative perturbation that will become more significant at high frequency than it is at low frequency. And in order to be robust to that, we need T to roll off. But with this best controller, it doesn't roll off. Okay? So delay puts limitations on what you can achieve. That's the main message I'm trying to get across here. All right? There are also some other structural limitations associated with a feedback interconnection. And these translate into the sensitivity functions having to interpolate particular values at the open loop zeros and poles. Okay, so in the notation that we've established, that corresponds to expressing the plant transfer function as a ratio of two polynomials B and A, and the controller transfer function as a ratio of two polynomials P and L. Okay, we can see that if Z is a zero of the open loop transfer function, and that could be because it's a zero of G or because it's a zero of C, and P is a pole of the open loop transfer function, which could happen because it's a pole of the plant or a pole of the controller, then the complementary sensitivity function evaluated at a zero of the open loop transfer function must also be zero. Right? So zeros of the open loop transfer function become zeros of the complementary sensitivity function. Right? And that means that the output sensitivity function at the zeros of the open loop will always be equal to 1. Okay. Similarly, the output sensitivity function, which tells you how sensitive the output is to output disturbances, it tells you how sensitive the error is to the reference. Okay, will have zero value when evaluated at an open loop pole. Okay, so at a pole of the plant or a pole of the controller. Okay, and so that will make the complementary sensitivity function equal to 1 at the open loop poles. All right. Similarly, if P is a pole of the controller, okay, so it's something that makes L equal to 0, then it makes the sensitivity function that relates the input disturbance. So that transfer function there, it will make it 0 at the pole. Okay, so these are so-called interpolation constraints, and they arise just by virtue of the structure of the feedback interconnection, which leads to these formulas for the sensitivity functions. Okay, so what might be some implications of these interpolation constraints? Okay, we'll see now how to use these to tell us about limitations on performance, okay, based on where you put the closed loop poles relative to the open loop poles and zeros. And we'll see, in fact, how to exploit these interpolation constraints to achieve performance specifications. In fact, we've already seen such a thing from the perspective of getting 0 steady state error tracking for step references or step output disturbances. Okay, so So let's look at the error signal. Okay, we know that that's the output sensitivity function times the reference. Okay. Now, if we have an open loop pole at S equals 0, right? In the example that we just saw, that was achieved by putting a pole S equals 0 into the controller. Okay. Then that's telling us S will be 0 at 0. Okay? If S is 0 at 0, S must have this form. It must have a factor S that you can pull out. Okay? In other words, if S is 0 at 0, then it must look like little s times another function, right? That has on the denominator the same thing as S, but on the numerator a polynomial of degree 1 less than the numerator of the left-hand side here, right? Because when I evaluate this at S equals 0, I get 0, okay? So that's what it means to interpolate this value. And so if I have a step reference, right, which will have Laplace transform looking like this, then the error signal will look like this. All right? Because this guy cancels this guy. And if the closed loop is stable, okay, you know that this function will be well defined in a right half plane, okay, so to the right of this line, that contains the imaginary axis, right? Because the singularities of this, which is now the Laplace transform of a signal, it's no longer a transfer function, right? Because we've multiplied it by an input, okay, to make it a signal again. But if the closed loop is stable, then all the poles of S, okay, lie in the left half plane, to the left of some line. Okay, that's what stability of the closed loop means. The singularities of S hat coincide, right? So if this is well defined to the right of a line to the left of the imaginary axis, then this is well defined to the right of a line to the left of the imaginary axis. And what do we know that means for a signal? It means that that signal will decay in the time domain. Okay, if the region of convergence for the Laplace transform of a signal is a right half plane that contains the imaginary axis, then the signal decays in the time domain. Right? So what that's telling us is that the error signal will go to 0. We will get 0 steady state error. Okay? By virtue of this, exploiting this interpolation constraint, right? By placing a open loop pole at S equals 0. Right? Perhaps by making it part of the controller. Okay? That doesn't work for input disturbances, right? For input disturbances, we need this function to be 0 in the right spot, right? not this function here. But we can make sure that this is 0 at s equals 0 by putting a pole into the controller. This can be 0 at 0 by either having the pole at s equals 0 in the controller or the plant. Okay, so from the perspective of getting 0 steady state reference tracking error, okay, the pole at s equals 0 can either be in the plant or the controller, right? But from the perspective of getting 0 gain at 0 frequency from here to here, you need to make it part of the controller. Okay, we'll see more about exploiting such constraints to achieve performance specifications a bit later on. Okay, what we're going to focus on now is implications of these interpolation constraints from the perspective of closed-loop performance. Okay, so given a signal h, okay, this integral just looks like evaluating the Laplace transform of h at s equals z, right, by definition of the Laplace transform. Okay, and that will be valid provided the value z is in the region of convergence for the Laplace transform of h. Okay, so this is just reminding you of the definition of something. Now, let's consider a feedback control system with these properties. Okay, so what we're going to do is put constraints on where the closed loop poles are. Okay, we're going to say that our feedback control system is such that the closed loop poles lie to the left of minus alpha, where alpha is some positive value. Okay, intuitively, we can think of the crossover frequency as being related to alpha. Okay, as we push the crossover frequency to the right, it's like making the complementary sensitivity function have a wider bandwidth. So you'd expect that to be consistent with something that is faster. So pushing the crossover frequency to the right will push this line to the left. Okay, the further this line is to the left, the faster the closed loop is. The further the crossover frequency is to the right, the faster the closed loop is. Okay. And in addition to that, let's suppose that we know that the open loop transfer function has a pole at s equals 0. And we're going to look at what happens when there's an open loop 0 at z and another pole at p. All right, so the reason for putting an open loop pole at s equals 0 is because that's a common thing to do so that you can get 0 steady state error for reference tracking or output disturbance rejection, as we just saw. Okay, but in addition to that, we've got another pole, okay, that sits somewhere to the right of this line minus alpha, and we have a 0 that sits somewhere to the right of this line minus alpha. Okay, so we know that by virtue of the interpolation constraints that we just saw, that the output sensitivity function evaluated at the open loop 0 must be equal to 1. The complementary sensitivity function inherits the open loop 0. Okay, the sensitivity function at the pole will be 0. The complementary sensitivity function at the open loop pole will be 1. And we know that s equals 0 is a pole. Okay, so at 0 we have these interpolation constraints here. All right. These interpolation constraints here make sure that Z and P are in the region of convergence for the Laplace transform of the error signal. Okay, because by virtue of this, okay, we know that this transfer function has a factor S that can be pulled out of the front. So when this signal here is a step, okay, we're just left with the S hat that we saw on this previous slide here, okay, which by virtue of this assumption, right, is something that's well defined everywhere to the right of this line. Okay, so if Z and P are to the right of this line, then they'll be in the region of convergence for the Laplace transform of the error signal. All right. So in view of that, we can write down these integral constraints. Okay, just that really just follow from the definition of the Laplace transform. And we can do this now because we've verified that Z, where we're going to evaluate this, and P, where we're going to evaluate this, are in the region of convergence for the error signal when the reference and output disturbance are step-like functions. All right? So just plugging that in, okay, we know that this integral must be equal to the value of the Laplace transform of the error signal evaluated at S equals Z. Okay? Just by definition of the Laplace transform. But we know that E will be this transfer function times the step input. Okay, and when we evaluate that at Z, we get this. But we know that SZ is equal to 1, so we've just got this. All right? Now, if we look at this integral, okay, where we've changed the exponential weight now to correspond to the pole that sits to the right of here somewhere, then we get this constraint here, right? This is just the Laplace transform of E, evaluated at S equals P. We've verified that P is in the region of convergence when the input is a step, okay? By definition here, that will correspond to this, but we know that S at P is equal to 0, so that gives us this constraint here. So what can we infer from these constraints? Well, these constraints are integral constraints on the error, okay? Now, we've got weighted integral constraints on the error. Let's think about what the weights are. Well, the weights are always positive for all t, right? Because e to the x is always a positive number for all x, right? So no matter whether z is positive or negative, this is always positive. So we've got a positive weight in both cases. All right. Now, what we're looking at is the error signal. The error signal is the difference between the reference and the measurement of the output, right? So in the time domain, we're saying that the error signal is the difference between R and Y. Okay, and we're looking at a situation where R, as a function of t, looks like this. It's a step. Okay, so it's changing from 0 up to 1 or some other constant value. All right. Now, if y is initially at 0, right? So if y is initially at 0, which is consistent with the reference being 0 before time 0, then what's going to happen to the error signal? The error signal will eventually be positive, right? Because this has become 1 and this is 0. So initially, the error jumps up to become positive at time 0. Okay, so it starts off positive. Now, let's look at these constraints. In the case that z is a negative number, it's saying this weighted integral of the error signal must be a negative number. How can I get the integral of the error signal to be negative overall when I'm starting off positive? Well, the error at some point must become negative, right? Such that this happens with this area being more than this area once I've weighted this by an exponential, which in the case that z is negative is in fact something that's blowing up, right? Giving more weight to this stuff than to the stuff at the beginning. Okay? So this constraint is telling you that when z is negative, right? So in other words, when the 0 sits here, okay, then the error must change sign. Okay? What does it changing sign from initial positive value to become a negative value so that we can satisfy this constraint mean? Well, it means at some time, okay, the error is negative. How can we get a negative error? We can get a negative error when y is bigger than r. All right? So in other words, we're going to get some overshoot in the response. Y is going to go past the reference. Okay? So we end up being able to draw this sort of conclusion here. All right? So if Z is a negative real number, the error must change sign, okay, which implies there's going to be some overshoot in the response. Okay? All right, let's do a similar thing. You could do a similar thing for using this constraint, right? So if we know that P is a positive value, okay, so it doesn't matter whether it's positive or negative, we're still going to get overshoot, right? Because we need the integral to be 0, right? And if we're starting off positive, the only way we're going to make the integral 0 is by going negative for some time. So you're always going to get some overshoot, all right? Now, let's consider the case where P is much, much larger than alpha. So that's going to put P in the right half plane, okay, and further away from the imaginary axis, right, than alpha. Right? The amount of time that it takes the error signal to decay is determined by alpha. All right? And if P is much, much bigger than alpha, then this exponential weight is going to decay much, much faster than the time it takes the error signal to decay. Right? Which is going to put much, much more emphasis on the first bit of the error in terms of satisfying this constraint. Right? Because this is going to 0 very, very quickly. Right? And so in a situation where P, the open loop pole, is in the right half plane and further away from the imaginary axis than the slowest pole of the closed loop, then you're going to have either very negative straight away or lots of oscillations at the start of the response in order to satisfy this constraint. Okay? So if you want to avoid that, you've got to make sure that you don't have a situation where P is much bigger than alpha. Whoops. All right, we get that, where lots of stuff has to happen in the beginning, right, in order to satisfy the integral constraint, by making sure you don't have that situation, right? How can you ensure that that's the case? Well, make sure that alpha is bigger than P if you have a right half plane pole. Okay? How can we make sure that happens? By pushing alpha further to the left, so that this line ends up being further away from the imaginary axis than the unstable pole. Pushing that to the left is often consistent with pushing the crossover frequency to the right. All right? And that's what this is about here. It's saying, well, if we want to avoid this sort of thing, right, limit the amount of overshoot or limit how oscillatory the response is at the start of the transient, when you have an open loop pole in the right half plane, make sure that the loop gain crossover frequency is set greater than the real part of the fastest pole. So in other words, it's putting a lower bound on the crossover frequency when you have an unstable pole. Okay? If Z is a positive real number, then the integral constraint that we used here, it isn't useful, okay? Because you're saying this integral of something that starts off being positive has to end up being positive. Okay, so you really can't draw any conclusions from that. But we know that the complementary sensitivity function will be 0 at 0. Okay, so that's like having a transfer function, right, with all poles to the left of this line and a 0 in the right half plane. And if that 0 is closer to the imaginary axis than the slowest closed loop poles, we know we can get lots of undershoot, right? We've already seen analysis that shows that when you have right half plane zeros that are closer to the imaginary axis than the slowest poles, you get lots of undershoot. All right? So if you don't want lots of undershoot, when you have a right half plane open loop 0, then you've got to make sure that alpha is closer to the imaginary axis than the right half plane pole. Right half plane 0. Okay? How can we ensure that? By bringing alpha closer to the imaginary axis, by bringing the crossover frequency down. Okay? Which gives us this rule of thumb, if you like. Okay, so the point of this analysis is to identify these sorts of potential trade-offs, right? This is saying if I've got an unstable right half plane pole, I've got to have a sufficiently high crossover frequency if I want to avoid, bad transients in the step response of the closed loop, right? This one is saying if I have a right half plane 0, I can't make the closed loop too fast, because if I do, I might get lots of undershoot, which is typically undesirable. Okay, so there's a point to this analysis. It's not very complicated analysis. It's really just based on the definition of the Laplace transform, which leads to these integral constraints, which then leads to these, guidelines for design in different cases. Okay. All right, this is another example of an integral constraint, okay, but it's a frequency domain integral constraint now, as opposed to these time domain integral constraints that we've seen. All right. It follows from Cauchy's integral theorem. Okay, let's not worry too much about what that is. It's about integrating analytic functions along closed contours, and if the function's analytic in the region on the interior of the contour, then the integral around it must always be equal to 0. Okay, that's what Cauchy's integral theorem says. Okay, so if we apply that to this analytic function, which corresponds to taking the natural log of the output sensitivity function, right? So if the closed loop is stable, then this function will be analytic in the right half plane, right? And what we're doing here is like integrating, along a contour that contains the right half plane. And because this function is analytic, all right, we end up with 0 integral, okay, by virtue of Cauchy's integral theorem. Okay. Now, what are the implications of this integral constraint? Here we got some integral constraints and we drew some conclusions, what they mean in different situations. All right. What conclusions can we draw from this integral constraint? Well, the sensitivity function, the output sensitivity function, is typically small at low frequencies, right, which is consistent with low frequency reference tracking, low frequency disturbance rejection. Okay, and it becomes 1 at high frequencies, because at high frequencies we want T, the complementary sensitivity function, to be small to give us low sensitivity to measurement noise, low sensitivity to modelling error. And if T is small, S will be 1, because S plus T is always equal to 1. All right? So S typically has this sort of shape across frequency, where it's small at low frequencies and getting close to 1 at high frequencies. All right? And this integral constraint is saying that when we integrate over frequency, okay, we must get 0. In other words, the area here must equal the area here. All right, I'm just integrating a curve because, on a log plot, right, and that's what we're integrating. We're integrating the log. Gain of 1 is 0, right? We've got a sensitivity function that does this, right? So this is negative, right? So we integrate that, you get a negative number. We integrate this, we'll get a positive number, and they have to add up to 0. Okay, so what's the implication of that? The implication of that is I've pushed this down, right, by, for example, increasing the gain of the loop, okay, then this must go up. All right? So getting better performance at low frequency might result in worse performance at high frequency. So this is often called the waterbed effect, all right, or conservation of sensitivity dirt, as this picture indicates. Pushing it down here pushes it up here. all right? And if you have an upper bound on the loop gain crossover frequency, which will correspond to something around here, all right, then you are forcing this beyond the crossover frequency. You're forcing S to be 1, right, because T is becoming small. All right, so if I've got an upper bound on where this is, right, so that's like putting an upper bound, a bound on when this S will become equal to 1, and I've got all of this that has to be balanced out. I can get large peaks in here as required to balance these two out. Okay, so that's another example of a structural limitation. Right? There's effectively all these things are saying there's never any free lunch. If I gain something over here, I'll lose it somewhere else. Right? And so what I'm trying to do is make you aware of these sorts of trade-offs. Okay? Because design, in the end, will be about balancing those trade-offs against each other. All right? So I think rather than rush through the internal model principle, I think we'll leave it there for today.
The angle of the delay function would be minus 2 omega. What would be the magnitude?
1.
So
Magnitude of, e to the j phi is that, so that's the angle phi. So as I change phi, I just move around, but the magnitude is 1. Yeah?
So irrespective of the power, for example, the same thing, if I have a 2 j omega phi, then the magnitude would be 2.
Yeah.
Instead of being 1.
Yeah. That's why we always write complex numbers. If I have a complex number, I can always write that as the magnitude of this, right? And the phase, right? So it'll be a squared plus b squared, right? And this will be, arc tan, of the imaginary part divided by the real part. Yeah. Make sense?
Thank you.